Hello everyone, welcome to Algebraic Calculus 2, and I'm Norman Wahlberger. Today we're going to talk about subderivatives, which are an important alternative to the usual derivative story, very closely connected, that come up naturally when we think about Lagrange's approach to Taylor expansions. So Taylor expansions is sort of a central topic in classical differential calculus. It allows you to expand a function around a point in terms of a power series. And Lagrange, Joseph Louis Lagrange, who was really Europe's most eminent mathematician after the passing of Euler, he took Euler's approach, which actually almost sort of follow on from Newton's approach, and developed it even in a more algebraic way, where he was able to think about what these Taylor expansions were in a quite a very simple algebraic way. Unfortunately, the direction that Euler and Lagrange envisioned didn't catch on in European mathematics as much as we might think, given that these were really the two dominant mathematicians of the 18th century. And we'll have to talk about that because that's an important link for us, because we are really interested in their approach. And in some sense, we're trying to push what they have done and bring it up to the modern time and show you that it's actually a very viable and powerful alternative to the current way of thinking, which is, in my view, rather waffly when it comes to a lot of these things. So what we're going to do is we're going to ground the discussion in polynumbers with a view of moving towards polyseries if we do things correctly. Okay, so let me remind you the usual derivative as we've set it out in the Algebraic Calculus 1 course is due to Faulhaber. It's a Faulhaber derivative, which is purely a formal operator on polynumbers defined by that d of alpha to the n is n times alpha to the n minus 1, where n is a natural number. And then it's extended linearly to general polynumbers. And then we can also talk about powers of the derivative, d super k. So let's run through an example or two. So if p is the polynumber 2 plus 7 alpha plus 3 alpha squared plus 4 alpha cubed minus 6 alpha to the fourth, then the derivative of p, d of p, and sometimes we'll write d bracket p like this, and if it's clear enough, we'll just dispense with the brackets and write dp. Okay, so the derivative of this, we all know how to do that. That's 7 plus 6 alpha plus 12 alpha squared minus 24 alpha cubed. Now, if we take the second derivative, d squared of p, well, that's the derivative of the derivative, then the 7 disappears. We get 6 plus 24 alpha minus 72 alpha squared. A third derivative is then 24 minus 144 alpha. Fourth derivative of this is just minus 144, and all subsequent powers of the derivative give 0. Okay, so this is the usual story of the powers of the derivative. We're going to want to think about a slight alteration of this. Okay, so key definition. For k a natural number, the subderivative d sub k is defined on polynumbers by the following. If p is a polynumber, then d sub k of p is the usual kth power of the derivative on p, but divided by k factorial. So we're just normalizing the power of the derivative to get the subderivative. When k is 0, which is included here, k factorial is usually deemed to be 1. And so this is just d to the 0 of p, which is p. Okay. So let's see what this small alteration does for us, right? So these subderivatives are sort of smaller than the usual derivatives or powers of derivatives because we're dividing by these k factorials. So that pulls down the sizes of the coefficients that are involved. Let's look at exactly the same example that we had previously with this p here. Then d sub 1 of p is the same as the derivative of p, because that's just the derivative 7 plus 6 alpha plus 12 alpha squared minus 24 alpha cubed that we've already seen. But now the second derivative, okay, is 1 over 2 factorial, or 1/2, of the second derivative. So if we take the second derivative, remember we get 6 here, so we have to divide that by 2. That gives us 3. Plus 24 alpha divided by 2 gives us 12 alpha. Minus 72 alpha squared divided by 2, we get minus 36 alpha squared. How about the third subderivative, d sub 3 of p? Well, according to the definition, this is 1 over 3 factorial times d cubed of p. But d cubed of p is d of d squared of p, and d squared of p is the d2 of p times 2. So we can write this in terms of the previous one that we've already calculated, namely d sub 2 of p, and write it as 1/3 of the derivative of d sub 2 of p. Okay, so a factor of 2 has canceled from that 6 to give us 3. So we just have to take the derivative of this one and divide by 3. Okay, the derivative of that is 0. The derivative of this is 12. Divide by 3, we get 4. The derivative of this is, the 2 comes down, 72. 72 alpha minus 72 alpha. Divide by 3, we get minus 24 alpha. And what about the fourth derivative? Well, the fourth subderivative, d sub 4, is going to be 1/4 of the derivative of d sub 3. If we take the derivative of this thing, we get minus 24. If we take 1/4 of it, we get minus 6. So here are the subderivatives of this polynumber. And then if you compare that with the derivatives, by which I mean the higher powers of the derivative, you see that the expressions are somewhat more manageable. We're not getting such big numbers. But that's not the main reason why we're interested in these things. So before we move on to the motivation for these things, let me show you a pretty cool way of actually calculating these things using some linear algebra. So let's look at the kth subderivative of the pure power alpha to the n. By definition, this is 1 over k factorial times the kth derivative of alpha to the n. Now, what's the kth derivative of alpha to the n? Well, you have to differentiate it k times. So the first time you differentiate, an n comes down and the exponent lowers to n minus 1. The next time you differentiate it, the n minus 1 comes down and the exponent lowers to n minus 2. After you've done it k times, you will have a factor n times n minus 1 times n minus 2 down to n minus k plus 1. And the power of alpha that remains is n minus k. So if we take that numerator that I just told you about and divide it by k factorial, that's exactly a binomial coefficient. It's exactly n choose k. Remember, n choose k can be thought of as n factorial over k factorial times n minus k factorial. But the n minus k factorial can be canceled out from the n factorial to give us this product n times n minus 1 times n minus 2 all the way up to n minus k plus 1. All right, so that's when you have still a k factorial in the bottom there. That's exactly what you're getting when you differentiate this thing k times with this thing here. Now, we've also seen that this binomial coefficient has an interpretation in terms of the Harriot matrix, okay, sometimes called the Pascal matrix, okay, but we're generally liking to think about it as the Harriot matrix, especially when we're especially interested in the columns of this thing, which are the Harriot bases sort of sequences. So h sub k of n is the kth column here, okay, as a function of n. And so this formula here allows us to sort of redo that calculation, and I want to show you a sort of a nifty alternate way of calculating the derivative of, or the various subderivatives of this polynumber 2 plus 7 alpha plus 3 alpha squared plus 4 alpha cubed minus 6 alpha to the 4th. So I'm taking this Harriot matrix, and I'm taking another matrix, which is a diagonal form of this polynumber that we're starting with, just putting the coefficients down the diagonal and zeros everywhere else. And consider what happens when we multiply these two matrices here. When you multiply a matrix with a diagonal matrix on the left, okay, then what happens is that each of the rows of this matrix gets multiplied by the corresponding factor on the diagonal. So if we look at what happens in this third row, so that one gets multiplied by 3. this, that one gets multiplied by 3. This, that gets multiplied by 3. That entire row gets multiplied by 3. Similarly, this entire row gets multiplied by 4. This one here gets multiplied by 7. This one gets multiplied by 2. And this one here gets multiplied by -6. And now we can see that actually the columns that we're getting here are essentially the subderivatives of the original polynumber p. They're the ones that I just calculated for you on the previous slide. But we have to sort of adjust our power of alpha in just a small way. So we have to kind of go down like this. Okay. So starting each of these columns with the diagonal entry. So this second column here corresponds to the subderivative d sub 1, which is the same as the derivative. And we read that as 7 plus 6 alpha plus 12 alpha squared minus 24 alpha cubed. This next one here, corresponding to d sub 2 of p, we read it as 3 plus 12 alpha minus 36 alpha squared. And I'll leave it to you to check. Make sure that you do check that this is actually valid, that it works. And it's basically because of this formula here. This is just a sort of an interpretation of this formula. So this is very nice. It means that we can calculate a lot of subderivatives very quickly, okay, by just working with the appropriate sized Harriot matrix. Now, if we had a bigger polynumber of higher degree, well, then this would have to be expanded. We get a bigger matrix over here, and we would correspondingly have to use a bigger part of the Harriot matrix, which is actually an on matrix, right? Because it actually goes on down and to the right. So this is just the top corner of it. So now I need to explain to you why subderivatives are really such an important tool for us to understand the differential nature of curves. Okay, that's what the differential calculus is about. It's about understanding what happens to a function, or better yet, to a curve, locally, near a particular point. And there's a sort of a sequence, a hierarchy of better and better approximations that we can look at, starting with a constant approximation, which is just the value of the function or the curve at that point. And then a linear approximation, which is like a line, or then maybe a quadratic approximation, which is typically a parabola, or a cubic approximation, which is a cubic curve, etc. Okay? And it's this hierarchy of approximations to a function or a curve at a point, which is the essence of the differential calculus. So I want to remind you of that because it's really important that we understand this basic story. Here is a curve. It's given by a polynumber. The polynumber is p is 2 plus alpha minus 3 alpha squared plus alpha to the 4th. So what we're seeing over here, the graph here, is y. Okay, y is that axis there. X is this axis. Y is p of x. All right? So we're cooking up a graph corresponding to the polynumber. Of course, we're only looking at part of this graph in the range that you can see, but okay. And what we're able to do really easily from the polynumbers form is to read off information about the local nature of this curve at that particular point, at the point 0, 2, at the point that corresponds to the x-coordinate being 0. What can we read off from that? Well, we can read off, first of all, that the value is 2. So the constant function, which best approximates the function at that point, is the constant function y equals 2. Then going a little bit further, taking the linear term into consideration, we get 2 plus alpha. That's like the graph y equals 2 plus x. Well, that's a line whose slope is something like this. Okay, my graph maybe doesn't show it, but that's what the tangent line to the curve at that point looks like. We go a little bit further over here, we pick up the quadratic term, then that gives us a quadratic approximation, which is a parabola. perhaps in green. Okay, parabola is going to be okay. I don't know, something like maybe something like this. All right. Okay, good. Now, but that's a lot of information, but it's only with respect to that point, which is rather limiting. What we want to do is have a technology that allows us to pretty smoothly extract local information at general points on the function's graph or on the curve. For example, perhaps at this point here, 1, 1. We plug in 1, we get 3 minus 3 plus 1. We do get 1, so this point 1, 1 is really a point on the curve. And we might want to know, what's the tangent like that? Is that actually at the bottom? Is there a local minimum there, or maybe not? What's a quadratic approximation? What's a cubic approximation, etc.? Okay, so our strategy to do that, okay, and it's a really important strategy, so let me remind you what we talked about last time. Our strategy is to convert this problem to the previous problem that I've just been talking about by essentially translating the entire graph so that this point that we're interested in ends up being over the point when x is equal to 0. So we have to translate by 1 over in the x direction to move that point over here. So that's accomplished by this little algebraic transformation, that we look at the curve given by the equation y equals p of x plus 1. Then when x is 0, for this curve, we're picking up p of 1, which is over here. Right. So this has the effect of taking the curve and translating it by 1 to the left. So it's translated. Notice the x plus 1 here affects a translation to the left, not perhaps naively as you might think to the right. So what does that shifted curve look like? Well, I'm going to just sort of do it ballpark here. Maybe I'll do it in blue, okay? So I'm going to maybe do it dotted. I'm going to try to just translate this in my mind, so a little bit artistically here. Whoops, sorry, we're going down here. Then we're going to go through here, and then we're going to go up here, and then we're going to come down here, and go down here, and then we're going to come up. All right? So that dotted thing in blue is supposed to be the translate of the original curve in solid blue. And here is its form. We just replace the alphas here with, say, x plus 1. 2 plus x plus 1 minus 3x plus 1 squared plus x plus 1 to the 4th. And now some algebra has to be done. We have to expand this out so that it ends up in the same form as our original kind of function, as a polynumber in the standard form. Of course, our computer can do this in a flash. This is something that computer algebra systems are totally good at, but for us, we do have to do a bit of expansion, binomial theorem prominently being utilized. When we do it, here's what we get. We get 1 minus x plus 3x squared plus 4x cubed plus x to the 4th. So what we can conclude from this is that this dotted blue line at x equals 0, it's given by 1. In other words, a sort of an approximation to it at that point there is this constant value 1. That's just the value of the function. If we look at the linear terms, we get 1 minus x. What does that look like? That's a line, negative slope. That's a line that looks like this. Okay. So you can see my graph is not exactly correct. This line here, passing through that point there, should be the tangent to it. Okay, then if we want to pick up the quadratic terms, 1 minus x plus 3x squared, we could graph that. Then we get a quadratic approximation to this thing, okay? I don't know what it is, maybe something like this, maybe something like that. And then, in fact, we could also pick up a cubic approximation, which I won't attempt to draw, but it might be some kind of cubic that approximates this dotted blue line pretty well there at that point. So the tangent line, at least we can read off, is y equals 1 minus x, while the tangent conic, this green one, has the graph y equals 1 minus x plus 3x squared. We're just truncating. Okay? Same kind of thing that we did up here. Now, these are the tangent line and tangent conic of this translated curve. To get back to the original question, because originally we're interested in the original blue curve at that point, we need to translate these various things that we found back to the right. How do we do that? Well, we do the opposite of what we did over here. Here we replaced x with x plus 1. Now to go back, we replace x with x minus 1. That affects a shift to the right. So for example, the tangent line will be y equals 1 minus, we take this equation, but replace the x with x minus 1 for a total of 2 minus x. So 2 minus x, what does that look like? Well, it has slope minus 1. When x is equal to 1, it has value 1. So that's that line right there. And in particular, we see that that point there is not a local minimum because the slope of the tangent is not 0. Okay, but the graph that I drew was not too bad. What about the tangent conic at this point? Well, we have to take the tangent conic here, that green one there, and translate it. So replace the x with x minus 1. 1 minus x minus 1 plus 3x minus 1 squared. Calculate that out. We get 5 minus 7x plus 3x squared, which, if we graph it, let me just check that it goes through 1, 1. If x is 1, 5 minus 7 plus 3, that is indeed 1. So it does pass through there. It'll probably be okay, something like this. Whoop, okay, that wasn't very good, but anyway, it'd be a parabola opening upwards, passing through that point there. Okay, so really important, a couple of ingredients here that we've done, right? First of all, we understand that finding tangent curves to a graph like this is easy when the point in question is sitting over x equals 0. That's the key thing, because then we're just truncating. So for the general point, what we do is we translate first to move our curve over so that the point in question is at x equals 0. And we do that by a translation like this. Then we expand and do the appropriate truncation to find the tangent line or the tangent conic or the tangent cubic, whatever we're interested in. And then we have to translate that back. So having gotten one of these things, the tangent line or the tangent conic, we translate them back by replacing the x, in this case, with x minus 1, the opposite of what we did initially. And that gives us tangent lines, tangent conics, tangent cubics, etc., to the point that we're originally interested in. Okay, so please make sure that you understand very, very well what I've done on this slide. Okay, this is the the essence of a lot of differential analysis. Okay, so really important. Go over it. Of course, once the course is started, you'll be able to get lots of examples, lots of work problems, etc. But in the meantime, you can work through things yourself. Work it out yourself. See how it actually works in practice, especially getting a hold of the difference between translating this way and translating back. So remember, my aim is to explain to you why subderivatives come in. So we'll see that here now by going back to that example that I just showed you in a special case. And let's look at it a little bit more generally. Okay? Not with specific numbers, but rather more generally where we have variables instead. So we'll start with the same polynumber, 2 plus alpha minus 3 alpha squared plus alpha to the fourth, graph something like this. And now we're thinking about, well, what is the local behavior of this graph at some arbitrary point where the x coordinate, or maybe the alpha coordinate, maybe a little bit more appropriate, is beta. Okay, before it was 1 in that previous example. What if it's just a general point, beta? What happens? So we want to do the same calculation that we just did, but more powerfully with a general number, in other words, a variable number, or better yet, a polynumber replacing a particular number value. So this is a theme that will be happening over and over. We often want to extend our arithmetic from talking about numbers to talking about polynumbers. More general, more powerful, a bigger point of view. Okay, so let's do pretty well exactly the same kind of thing that I did before. So what did we do? First of all, we translated this function, right? Instead of p of alpha, we're considering p of alpha plus beta. Okay, so we just take this expression, replace the alphas with alpha plus beta. And then we have to expand it out. So again, binomial theorem, etc. It's a little bit more maybe abstract because now there's betas floating around. And I'm going to write the result as a polynumber in alpha. So I'm going to sort of record things at the level of alphas. There's the constant term, which doesn't depend on alpha. The things that involving just alpha, well, there'll be a 1, there'll be a minus 6 beta from here, and there'll be a 4 beta cubed coming from that term. The alpha squareds get coefficient minus 3 plus 6 beta squared, and the alpha cubed, 4 beta times alpha cubed, and there'll be a single alpha to the 4th. Okay, so that's the equation, if you like, of a translated polynumber where we translated over, so that the point that was sitting over beta is now sitting over 0. So at this stage here, where we could read off tangent curves, okay, the constant approximation, the linear approximation, the quadratic approximation, the cubic approximation, etc. But then to take those and then shift them back to the point in question, we have to perform another translation. And pleasantly, we can do that all at once. We don't have to do it for each individual ones because it's the same story. We're basically just going to replace the alpha here with alpha minus beta. The opposite of what we did here. We replaced alpha with alpha plus beta. Now we're replacing alpha with alpha minus beta. So we get the following identity. You see, if in this thing here, if you think about replacing alpha, this is an identity, right? P of alpha plus beta is this expression. If you think about replacing alpha, every alpha, replace it with alpha minus beta, it will still be an identity. But then over here on the left-hand side, you'll have alpha minus beta plus beta. That's just alpha. So on the left-hand side, you will have P of alpha. And on the right-hand side, you'll have this quantity here that's repeated, plus this expression times alpha minus beta, plus this expression times alpha minus beta squared, plus the 4 beta times alpha minus beta cubed, plus alpha minus beta to the 4th. Now this is an identity. What does that mean? It means that if you actually expanded the right-hand side, expanded everything out, okay, got rid of all the brackets, expanded all these powers, expanded everything out, what you would end up finding is that everything would simplify and you would just end up with these 4 terms, 2 plus alpha minus 3 alpha squared plus alpha to the 4th. This is an identical expression to the original polynumber, but that's what the left-hand side is telling us. But now we've rewritten it in such a way that it's expressed in terms of powers of alpha minus beta. Alpha minus beta to the 0, alpha minus beta to the 1, alpha minus beta squared, alpha minus beta cubed, alpha minus beta to the 4th. And geometrically what that does for us is it allows us to read off automatically the various tangent curves to the original polynumber P at the point beta, at that point there. So if we want to know what is the tangent line to the original curve at that point, right there, this line right here, what we do is we just look at this and say, okay, the linear part, we're truncating to degree 1. That would be just this plus this, and all of this would be removed. And then this here is a linear equation in alpha. It's a linear polynumber in alpha with the coefficients that depend on beta, the point that we're talking about. If we wanted a quadratic approximation to the curve at this point, so some parabola that's pretty close to the curve here, well, then we would take this term plus this term and this term. We would truncate, do a t sub 2 truncation and remove everything of degree higher than 2. See, we're getting more information by doing this in this more algebraic way here, because we can see sort of more clearly. There's more information, and that's useful for us. But especially important is now because of the following observation. Okay, critical observation is that these coefficients of these various powers of alpha minus beta here that are appearing, namely this one here, this one, this one, this one, and this one, are all just the subderivatives of the original polynumber evaluated at beta. You see, this thing here is just the original polynumber, right, evaluated at beta. This expression here is just the derivative of this. Derivative with respect to beta. Okay, yes. So the beta goes to 1. There's a minus 6 beta, 4 beta cubed. So this is the derivative of that. But it's also d sub 1. It's also the subderivative of this. And what about this next one? Well, if we take the derivative of this, we get minus 6 plus 12 beta squared. That's not what's happening here. We're getting minus 3 plus 6 beta squared. We need to divide the derivative of this thing by 2. That's a subderivative. This is the second subderivative of this quantity here. This is the third subderivative, and this 1 that's appearing here is the fourth subderivative. So this is a beautiful, beautiful thing. That means that somehow magically, just by appealing to our understanding of subderivatives, we could write down an expression like this without having to go through this trouble that we were talking about, of taking the curve, making a substitution that affects the translation, rewriting it, and then making another translation back. We can rewrite this or get this expression just by writing down an expression starting with the original polynumber and having these coefficients as just the subderivatives of the original expression, admittedly evaluated at beta. This is, in some sense, Lagrange's insight. Lagrange understood that you could get what's effectively called a Taylor expansion, not by looking at limits and the standard sort of infinitesimal approach, which at that time was the prevailing way of thinking about derivatives, but purely algebraically. And this algebraic thing ends up sort of capturing the derivative story, but more pleasantly if you use the language of subderivatives. Okay, so there's really an identity kind of floating around here, and we're going to call it the Lagrange Taylor identity. Taylor, who was one of the founders of the Taylor series kind of expansions, although actually the English, perhaps Scottish mathematician Gregory probably introduced these things actually before Taylor. But anyway, Lagrange then came around and gave this sort of algebraic point of view, and I'm going to call it Lagrange Taylor identity. And here it is, that for any polynumber p of degree n, okay, the polynumber p can be written in this bipoly number fashion. In other words, not just involving alpha, the polynomber alpha, but also the other bipoly number beta. And if you don't know about bipoly numbers, well, it means that you haven't watched the algebraic calculus course carefully enough. So please have a look at that, where we talk all about the crucial role that these polynumbers and bipoly numbers play. And alpha and beta are not just abstract variables, right? They're specific arrays of numbers, so it's all cut and dried. Okay, what is the identity? It's that p equals p of beta plus d1 of p at beta times alpha minus beta, plus and so on up to d sub n of p at beta alpha minus beta to the n. So we have increasing powers of alpha minus beta, and the coefficients of the powers of alpha minus beta are the corresponding subderivatives of the polynumber evaluated at beta. And let me remind you that when I write p, it's really p of alpha because the standing convention that is that a polynumber is expressed in terms of powers of alpha. That's our basic polynumber. Okay, I want to give you a proof of this rather remarkable identity, which shows that it's actually somewhat elementary, and it comes down, as many things do, ultimately, to the binomial theorem. So the identity is linear in P. In other words, all these things that are happening here are linear in P. In particular, the subderivatives are linear. If you take the subderivative of sum P plus Q, you're getting the subderivative of P plus the subderivative of Q. If you take the subderivative of lambda times P, you're getting lambda times the subderivative of P, etc. Okay? So it's linear in P. And so that means that it suffices to prove it for the case of having a basis element of our polynumbers, some pure power alpha to the n. Okay, so let's think about what happens when P is just alpha to the n. So then this over here is alpha to the n. P of beta will be beta to the n. The derivative, or the subderivative d sub 1 is the same as the derivative, will be n times beta to the n minus 1. There will be an alpha minus beta here. The next term here, what will that be? Well, it'll be the second subderivative of P. So what's the second subderivative? It's the second derivative divided by 2. So the second derivative is n times n minus 1 times alpha to the n minus 2. And we have to divide by 2. So we get an n times n minus 1 over 2. That's just n choose 2. We have to then evaluate this thing at beta. So we get beta to the n minus 2 and an alpha minus beta squared appearing there. All the way up to the very last term here. Okay, the nth subderivative, what is that? Well, if we differentiate this n times, we're going to get n times n minus 1 all the way to 1. We're going to get n factorial on the top for the nth derivative. But we have to divide the nth derivative by n factorial because it's a subderivative. And so the coefficient becomes just 1. Okay? And so we just end up getting alpha minus beta to the n. So this is the expression that we need to prove. And we stare at it and we see, well, actually, this is just the binomial theorem. It's just an expansion of this. Beta plus alpha minus beta to the n. What's inside here is clearly alpha, so that's certainly alpha to the n on the left-hand side. And what we're doing is we're just sort of expanding this out in powers of beta and powers of alpha minus beta. Decreasing powers of beta, increasing powers of alpha minus beta with binomial coefficients appearing as the coefficients. Now there's a few alternate forms of this Lagrange Taylor identity that I need to write down. So here's the one that we've just proven. Okay, P or P of alpha is this expression. And here is just a rewrite of it where we just interchange the roles of alpha and beta. They're just polynumbers. The situation is symmetrical between them. So we just replace the alphas with betas and the betas with alphas. So the alpha minus beta here becomes beta minus alpha. That beta turns into an alpha. There's a beta minus alpha to the n. And then in our next rewrite, now we're going to take this one here and we're going to replace beta with alpha plus beta. With alpha plus beta. So we get P of alpha plus beta over here. This thing doesn't change. This doesn't change, but the beta is replaced with, so this beta is being replaced with alpha plus beta. So if you stick an alpha plus beta in here, you get alpha plus beta minus alpha. That's just beta. Okay, and so beta minus alpha becomes just beta. And so the next term will be d sub 2 of P of alpha beta squared all the way up to d sub n of P of alpha. And this thing becomes beta to the n. It's in this form here that perhaps it's the most common form of what's called the Taylor expansion of the polynumber P around alpha. And the idea is that, okay, traditionally we think, well, okay, alpha is some point, and we're interested in the function or the polynumber's values close to alpha, okay? So we augment alpha by some typical small amount beta, and then this is some kind of expression that explains how the value of this thing depends as you vary beta. It's a polynumber in beta with these coefficients that depend on the subderivatives essentially evaluated at the base point alpha. So the point is that all these coefficients here are only dependent on the nature of the curve exactly at alpha. Okay, just subderivatives at alpha. But that's enough to recover the values of the polynumber at neighboring points because of this remarkable identity. But in this context here, it's more general than that. This is an identity that does not depend on beta being small. Okay, there's no approximation going on here. This is an exact identity that's valid. Okay, I remember P is a polynumber of degree n. That was the assumption in the previous identity. Okay? P is a polynumber of degree n. In this case, this is an identity that holds for all alpha and beta. And in fact, it's not just for numbers, alphas and betas. It's really more powerfully for polynumbers, alpha and beta. So this is the classical Taylor expansion of P around alpha using subderivatives. So there's no factorials in the denominators that have sort of been incorporated in the notion of subderivatives. So we've covered a lot of material here, and it's I know a little bit non-standard, a little bit novel, but this is firmly in the direction of Lagrange's thinking. So Lagrange would have said, yeah, that's all in my book, okay? So this is a really powerful way of thinking, as we'll see. So there's much to learn. I'm Norman Wahlberger. Thanks for listening.